You get two quotes for motorized outdoor screens. They look identical in the brochures. One is $3,000, the other is $9,000. On day one of installation, both options roll down quietly, block the sun, and look fantastic. The physical shortcuts taken by the budget manufacturer are completely invisible. These quotes represent two entirely different engineering approaches. The premium price tag buys the specific physics required to survive a harsh local environment. This comparison graphic details how multiple environmental stressors, like UV degradation, salt corrosion, sudden gusts, and heat overload, attack the screen simultaneously. A high-severity climate will violently expose underspecified components within the first few months of use. Treating a motorized screen as a simple cosmetic upgrade rather than pieces of exterior architectural equipment guarantees financial regret. This radar chart maps out the Department of Defense's C3 to C5 environmental severity classification for coastal zones. These zones apply constant pressure through 4 extreme stressors: dynamic wind loads, an EPA UV index of 11 or higher, high coastal chlorides, and 88% morning humidity. Many homeowners operate under the dangerous assumption that a heavy-duty retractable screen doubles as a hurricane shutter. It does not. The Florida Building Code mandates that screen panels must be fully retracted when winds exceed 75 miles per hour. If the screen fails to retract, dynamic wind loads push the system past its limits, severely deforming the material and compromising structural integrity. If you buy a budget system that fails to put itself away safely, the resulting storm damage is entirely your liability. This comparison matrix highlights the long-term ROI difference between a budget setup and an engineered system. To understand the true cost, we have to look closely at the hardware. This interface map identifies the 4 specific junctions where stress forces these systems to fail: the motor, the sidetrack, the fabric, and the weather sensor. This line graph charts the internal temperature of a continuous run budget motor. Inside a dark housing cassette during peak ambient heat, the temperature spikes rapidly, crossing the catastrophic failure threshold and permanently killing the motor. Premium systems counter this with active thermal shutdown protocols. Certified SOMFI motors temporarily disable themselves to enforce a cooling period, preserving the hardware's operational life. Saving money on a budget motor up front ensures you will pay for a complete mechanical replacement shortly after installation. This cross-section illustrates our second failure point, the side retention track. Budget tracks rely on shallow aluminum channels holding on to a loose fabric edge. Under heavy wind pressure, that loose fabric begins to oscillate. The friction builds until the material violently rips entirely out of the shallow track. An engineered zip track solves this by mechanically locking a reinforced zipper edge inside a deep, heavy-duty channel. This design evenly distributes tension across the frame, locking the fabric in place and mitigating blowout risk. Utilizing cheap track extrusion allows the manufacturer to lower their material costs, but it transfers all high-wind blowout liability directly onto your shoulders. This degradation cycle diagram shows what happens to the fabric. Intense UV radiation aggressively breaks down polymer chains, causing extreme embrittlement and rapid loss of tensile strength. Combine that weakened fabric with wet-dry humidity cycles and coastal chlorides to create sticky, abrasive grind buildup. The inevitable outcome is a mechanical jam, where sagging fabric hits extreme friction and tears. This technical drawing of an L bracket highlights another vulnerability. Cheap fasteners and thin aluminum guides blister and warp under coastal salinity, forcing the track out of alignment. Surviving these conditions require heavy AAMA 2604 powder-coated finishes to maintain structural alignment, paired with named UV-stabilized architectural meshes. When a manufacturer hides the origin of their textiles and hardware behind vague marketing claims, they are masking performance risks that will destroy the system. Finally, weather automation. You expect the automated wind sensor to recognize a sudden storm and retract the screen to safety before the gusts arrive. This circuit board schematic reveals the hidden electrical cost of 88% morning humidity. Moisture infiltrates the poorly sealed housing of a budget receiver, causing internal condensation. This reaction timeline details the outcome. On the bottom path, the corroded receiver completely misses the radio command from the wind sensor. The system suffers a silent failure, and the screen is destroyed. The top path shows the engineered alternative. Systems utilizing IP44 rated outdoor sensors and active radio transmission ensure immediate, reliable motor retraction the second the wind limit is exceeded. A weather sensor is physically useless and incredibly dangerous if its housing cannot survive ambient humidity long enough to detect the wind. Let's map out exactly which system makes sense for your specific geography. This decision tree evaluates your needs based on environmental severity. In a mild inland climate, a budget system is a reasonable calculated risk, but in zones with stacking stressors like coastal salinity, severe UV, and storm fronts, relying on a budget system becomes a guaranteed liability. This overlay reveals the reality of the premium price. You are securing verified structural integrity, advanced weather resistance, and long-term environmental resilience. Outfitting a critical structural interface on the outside of your home requires equipment rated for the local elements. The cheapest motorized screen becomes the most expensive option on the market the second you pay for a motor replacement, clear a mechanical jam, or cover a denied storm claim.